Here we see the Pythagorean relationship in different ways. So sometimes we're going to add the two squares and square root to find the length of the largest square. Okay, sometimes we're going to subtract the big square minus the small square and then square root to get the side length of one of the shorter sides. So we're going to see the Pythagorean relationships in all sorts of ways. So sometimes with square roots, sometimes with the squares. And it's important to recognize when we're dealing with side length versus area. So the 3 and 8 here represent side length. The C represents side length. 3 squared is area. 8 squared is area. These two parts are area inside, but when we square root it, we end up with the side length. So let's calculate some of these here. So these ones, some of these are straightforward calculations. So if I can do 3 squared plus 8 squared equals C. And again, we want to make sure since this is an equation, we want to show left side, right side, and we want to make sure we're keeping track of all the terms line to line. So 9 plus 64 works out to be 73. So C is exactly square root 73. We can leave our answer like that, or we can work out the decimal value for this. And sometimes we need to know the decimal value too when we're doing measurement. So 70 square root 73 works out to be approximately 8.54. Okay, so here the 9 and 64 represents areas, 73 represents area, C represents side length, the 8 and 3 represent side lengths as well. So when I draw this out, I have a side length of 3, a side length of 8, I have an area of 64, I have an area of 9, and I have a square off the hypotenuse of 73 squares. Okay, so this is what the diagram looks like, and the length along that diagonal is 8.54. When I look at this next expression, so 12 represents a side length, 5 represents a side length, A represents a side length, 12 squared, 5 squared are areas, and the number inside the square root represents area. So it's going to look like this. So I have the long side 12, a shorter side of 5. So I do 12 squared, that's 144. And I'm going to take away the 5 squared, which is 25. That length is A. And this area inside here is going to be the difference between here. So if I subtract those, I get 144 minus 25 is 119 squares. Okay, so A squared is equal to 119. The length of A is when I square root it. So if I square root 119, I get A is approximately equal to 10.908, so I'm going to round that to 10.91. So that's approximately equal to 10.91. So that's what my diagram should look like for this expression here. This one is a little bit more typical in that we can see the area, the A squared, B squared, C squared. So I should be able to draw this out as 2 squared, 5 squared, and C squared. So this is going to be area of 4. I should end up with a square area of 25. So 4 plus 25 equals C squared. Okay, so that's going to be my C squared. So 29 equals C squared. Again, notice how I'm keeping track of all the terms when I write it algebraically. So C squared is equal to 29. Okay, so then there's my area. So if I want to find out C, I need to square root 29. And that's approximately equal to, when I square root 29, it's approximately equal to 5.39. Okay, so that's about 5.39. It's a little bit longer than the 5 side. For this one here, we can, again, a squared plus b squared equals c squared. So the c squared, or 8, the 64 represents the largest area from the hypotenuse. That's going to be 5, so 5 squared is going to be my 25 here. Okay, so I end up with a squared plus 25 equals 64. So those are all squares here. This square in here, when I subtract them, I end up with a squared equals 39. Okay, so there's 39 squares here. And the side A works out to be square root 39, which is approximately 6.24. So this length here is about 6.24. Okay, so this is where my value of A is the side length. So I need to square root that value. So here the side is 15. The B that I'm solving for is a side length. This 9 represents square root. So notice that's square root. So that must be side length. Okay, so when I draw this out, I'm just going to sketch it out here. The longest side is going to be 15. I have another side of length 9. My 15 squared, 225, represents an area. B squared is the unknown area here. Maybe I'll make this one 9. 81. Okay, so this is B squared is here, and that's equal to square root is equal to 9. Okay, so I'll just leave it like this for now. That's length B. If I want to find out the length of B, to do that I need to use the area here. So I need this area of 81. So I know that to get that algebraically, I can square both sides. So I get 81 here. So that works out to be 81. Okay, these circled bits are areas. I want to get B squared, so I have to subtract these two lengths. So 225 are these areas. So 225 minus 81. So algebraically it looks like this. I'm going to add B squared to both sides. Plus B squared. And I'm going to subtract 81 from both sides. So minus 81 minus 81. So I've kept this equation balanced. Okay, the right side and the left side are balanced. These cancel out, and notice that I end up with 225 minus 81 here. And notice I'm doing all my calculations vertically. I'm not doing them sideways. So I did 225 minus 81. That gives me 144. And that's equal to B squared. And that's what I should see here. Notice that if I were to do the calculation in the diagram, yeah, that B squared is 144. So if I want to find out B, I have to square root both sides. Okay, I want to go from area to side length. I'm square rooting. So B, the length of B works out to be 12 units. So that works out to be 12. Okay, I think I did the diagram in terms of the 9 looks longer than 12, but algebraically this is correct.